Page 3, working on the solutions for these absolute value inequalities from 15 to 26. Number 15. Absolute value of x is greater than or equal to 7. Greater than 7 is going to split into two things. X is less than -7 or x is greater than 7. Graph looks like this, where we have there's 0, there's 7, and there's -7. Open and head up that way because we're not equal to 7, we're not equal to -7. And there's the graph, the interval -infinity to -7. Open on both of those. Union 7 to infinity. And then the set notation, set of all x such that x is less than -7 or x is greater than 7. Like that. Number 16. X minus 7 is greater than or equal to 13. So this will split up into two things. X minus 7 is less than or equal to -13, or x minus 7 is greater than or equal to 13. Add 7, we get x is less than or equal to -6, or x is greater than or equal to 20. So the graph, there's 0, there's -6, and there's 20. This one is from there up. That one is from there down. So we get -infinity to -6. Union 20 all the way up to infinity, not including infinity, of course. And set notation looks something like this. X is less than or equal to -6, or x is greater than or equal to 20. Number 17. Here we have 5x plus 3 is less than or equal to 1 and greater than or equal to -1. Notice that this is a less than or equal to sign, so the distance talked about with this absolute value problem is constrained by 1, so the distance is going to be limited. So these numbers have to fall between 1 and -1. It's not an or statement, but is now an and statement. So we're going to subtract 3, subtract 3, subtract 3. We're actually solving two inequalities at the same time. So we get -4 is less than or equal to 5x is less than or equal to -2. Divide all sides by 5. Get -4/5 less than or equal to x less than or equal to -2/5. And if we put the little x and the braces right there, that's our set notation. Our graph looks like this. Here's 0, there's a -2/5, and there's a -4/5, and x is bigger than or equal to 4/5, and all the way up there like that. Interval notation, we go from -4/5 to -2/5, and we include both of those, so those are closed on the ends. Number 18. 3x plus 7 is less than or equal to -5. Now before we do this, we would split that up into two equations, less than or equal to -5 and greater than or equal to 5, but that's just not going to work. We know that a positive is never ever less than or equal to -5, so this is a no solution. We don't even need to do any problems with it. No graph, no interval notation, we're all good. No solution, also known as the empty set. Number 19. Absolute value of -2x plus 4 less than 18. Again, this is an absolute value. It's a less than 18, so this is a -2x plus 4 is less than 18 and bigger than -18. So subtract 4, subtract 4, subtract 4, and we get -22 is less than -2x is less than 14. Divide everything by a -2, and this becomes an 11, greater than we're dividing by a negative number, so this guy switches, and that guy switches, a -7. One way to double check that these have switched correctly is you'll notice 14 is bigger than -22. However, if we didn't switch them and we divided them, we'd have -7 bigger than 11, which is nonsense. We don't want to do that. So put a little X out there, put a little squiggle there, and it looks nice. It's in set notation. Here's the graph. Here's -7, there's 0, there's 11, and we are sandwiched in between those two numbers like that. We go from -7 up to 11, open on both of them. Number 20. This is 3x minus 5 is greater than or equal to 14. So the numbers that will work there are the numbers where 3x minus 5 is less than or equal to -14, or 3x minus 5 is greater than or equal to 14. One just like it looks and one with the negative. So we solve these and we get 3x is less than or equal to, add 5, and we get -9, which is x is less than or equal to -3. Or add 5 to both sides and we get 3x greater than or equal to 19, x greater than or equal to 19/3. And there we have our set notation, our graph. Here's 0, here's -3, and here is 19/3. And we are less than or equal to -3 or greater than or equal to 19/3. Luckily that's not an AND statement or we would have no solution. That's what actually happens on that one right there. Having something less than -5 and bigger than 5, you end up with this kind of situation. So interval notation, -infinity to -3, open, closed, union, 19/3 up to infinity. And there we go. Number 21. Absolute value of 6y minus 1 greater than 7. So this will split up into two equations. 6y minus 1 is less than -7, or 6y minus 1 is greater than 7. Add 1, we get 6y is less than -6, y is less than -1, or add 1 over there and we get 6y is greater than 8. Divide by 8, we get 8/6, or in other words, y is greater than 4/3. This is our set notation. Our graph, here's 0, there's -1, and there's 4/3. Open on -1 and open on 4/3. One headed down, one headed up. Interval notation is -infinity to -1, union 4/3 to infinity. Better change colors here for number 22. We have absolute value of -2x plus 7 is greater than -4. Oh, stop! We've got an absolute value with a negative on the other side. Something's going on here. This turns out to not be a no solution. Here we have this guy is definitely positive, and that guy's a negative number. Positives are always bigger than negative numbers. So this is not never, this is always. So all numbers. So we can write it like this: a set of all x such that x is somewhere in the real numbers. Definitely works. And that'll cover everything on the number line. The graph, you would just color in everything. The interval notation looks like this for all real numbers, because you go from -infinity to +infinity, all of them. All right, let's do number 23. 6m minus 5, absolute value of that less than 3. So it breaks up into two inequalities, but this one is a compound inequality. Anytime you have a less than, that means the absolute value is, the things inside the absolute value are trapped by those numbers. So now we're going to add 5 everywhere. So we get 2 is less than 6m is less than 8. And divide everything by 6. And we get 1/3 is less than m is less than 4/3. Put a little m there. And a graph. There's 0. There's 4/3. There's 1/3. And we are open between the two of them. There we go. And so the interval notation 1/3 to 4/3. Then we have up to number 23. Number 24, absolute value of 7 minus 2t greater than or equal to -7. Again, something's going on with this. We have a positive number over here. Is it always or never bigger than or equal to -7? It's always, no matter what you stick in here, and you can give it a shot. Stick in 17 or 39 or -50,000. When you take the absolute value, you'll get something positive, which is bigger than or equal to -7. It works. So, solution set is all numbers such that we're sticking in the real numbers right now. The graph, of course, there's 0, and it's just going to be everything in both directions. Interval notation, -infinity to infinity. Number 25. 7 minus 3r, absolute value of that greater than 10. Breaks up into two things where we have 7 minus 3r can be less than -10, or 7 minus 3r has to be bigger than 10. So writing one down just like it looks like, and then the one with the negative on the other end. Subtract 7 from both sides, and we get -3r is less than -17. r is bigger than 17/3. Again, we switch directions whenever we divide by a negative. Here we subtract 7, we get -3r is greater than 3. r is less than -1. So, this is an or statement between these two. And if we put these on it right here, good. So there's 0, here's -1, and there's 17/3. It says r is bigger than 17/3, so we do not include 17/3 in the answer. We go up, and it's less than -1. So we are down here like that. That's -infinity to -1. Open, open, union, 17/3. Again, this just means that that one particular number, 17/3, is not an answer. Up to infinity. And the last one, number 26. We have a positive number less than a negative number. That will never happen. We looked at it up here in number 18, and that is no solution. Can't happen. Bzz. Play again. So, officially, it looks like that. That is the solution set, the set that has nothing in it, called the empty set. And there we have it.